Hello, I think it's time to start. Good afternoon, or good evening, or good morning. This is the first tutorial in BPM 2020, and I'm Min Seok-song at Hostech, South Korea, one of the co-organizers of the tutorial. First of all, on the behalf of the organizers, Joseph Carmona and Hayo Reyes, thank you for joining this session. As you can see in the screen, the title of the tutorial is Information Systems Modeling, playing with the interplay between data and processes. We have two speakers, Dr. Atem Poliani and Dr. Yanmaten von der Werf. As you might already know, they are very active and talented researchers in our community. Atem is a senior lecturer at the School of Computing and Information Systems at the University of Melbourne in Australia. He got PhD degree at University of Potsdam in Germany. He has strong background in theoretical computing, computer science, software engineering. His research include information systems, distributed systems, process modeling and analysis, and BPM. Atem has published over 75 scientific papers and got several best paper awards. And what I remember is the one at the ICPM last year, the international conference on process mining. Congratulations again. And Dr. Yanmaten von der Werf is an assistant professor at the Utrecht University on architecture mining. That is combining process mining with software architecture. He received a dual PhD in computer science from Eindhoven University of Technology and the Humboldt University in Berlin. His research focuses on modeling, analyzing, and reconstructing interactions between components in large, complex software systems. He is interested in how formal methods can be used in practice to study the dynamics of large systems. Yanmaten is very active in both the process mining community and software architecture community. As you can see, their background, they are the ones who can talk about this topic, and I'm very happy to have them. So let's welcome Atem and Yanmaten.
Thank you, Min-Suk. Thank you for the introduction. So I will start the session and then Yanmaten will take over the second part. Ladies and gentlemen, so welcome again to this tutorial. Me and Yanmaten are very happy to host this session, and we are extremely excited to talk about our recent work on modeling of information systems. So we had the first idea that something needs to be done about joint modeling and analysis of data and processes back in 2017 when we met with Yanmaten. If Yanmaten, you remember, we met at Buenos Aires, the International Conference on Software Engineering, and we quickly found the points of attachment, as both of us were at that time, and actually also now, both of us are teaching modeling of information systems. And both of us felt, and actually continue to feel, a strong lack of theories, methods, tools for integrating basically information and process models of information systems. So if I go forward, it is nice to see that in less than 3 years after that our meeting, we have several papers with solid results now published on this topic and a comprehensive tooling to validate and demonstrate the ideas. And we also started using these tools and these ideas in teaching. So Yanmaten had a class last semester, and he'll continue teaching using this approach and tools in the semesters to come. And I will also introduce this into my teaching here in the University of Melbourne for starting from next semester in 2021, so first semester in 2021. So the plan for the next hour or so is I will make a brief introduction to the topic and start the demonstration of a simple web shop scenario And for this scenario, using our set of tools, to which we refer as an information systems modeling suite, we will build a model of information system. I will show you how one can develop and verify information model and its population composed of facts. And then Jan Martijn will take over and show you how one can build a process model, link process model with the information model, and then also simulate the resulting system using our ISM suite. And finally, towards the end of this session, I will highlight two problem areas, namely constraints that are valid when we look at information process model in isolation, but become redundant when we look at the interplay. And the second, balancing of the constraints between information and process model. So where do we want to put the constraints? Do we want to have them in the information model? Do we want to have them in the process model? And I think this is also a very valid problem to investigate. So, and then we'll open the floor for comments, questions, and discussions, and maybe suggestions. What can we look at and what we can study in this area? All right. So data and processes indeed interplay in information systems. This suggests that traditional ways of preparing nice and shiny information process models separately. So if you prepare models that are separately correct in terms of soundness, for example, in all possible normal forms, then linking these nice models can certainly miss some important aspects. So in an information model, we usually specify structure and semantics of information principles for querying and manipulating information, while in a process model, we usually capture tasks, decisions, ordering constraints, rules of how information is transferred between the task or it gets manipulated along the execution of the process. So let's take a look at a simple purchase process at a small organization that requires that before a product can be purchased, two suppliers need to provide a bid for that product. But then the best supplier will receive the order and deliver the product. So the process model is clearly sound, right? It is just a sequence of activities here. And we also have a corresponding information model. We capture it as an object role model or RAM notation. But, and if you don't know RAM, do not worry, I will walk you through an example of constructing a RAM model just in a second. So the main observation at this stage here should be that this object role model, this information model, is also correct, right? It's doesn't have redundant or conflicting constraints. And suppose that we now start executing the system that is defined by this process and information model, right? So if I click, I'll have this first token and I start executing the model. Well, I create an order and I'm now sending the bid to the suppliers, and I probably can have many, many more cases running through, but then the process gets stuck at that stage despite the fact it's sound. And if we start digging deeper on and trying to understand what is happening, we may notice that in our database, in our information model, well, every product is just supplied by one supplier. So we can just go satisfy that constraint. We just cannot achieve a state where we receive two bids from a supplier for the same product, because there are no products that's supplied by the two suppliers, right? That's not happening. Okay, you may say, well, we just need to wait. We wait until the supplier, we get a new supplier that supplies a product. Eventually, that supplier will bid. But of course, also here in the model, if I add a constraint that the product is supplied at most by one supplier, for example, think of such a hypothetical scenario that I want to model, the model will also be correct, right? There will be no redundant constraints, there will be no conflicting constraints. It will be just that we capture a different scenario at this stage. So the model will be still correct, but the system cannot progress as a whole, right? So we achieve this global deadlock. So briefly, what we will talk about. So in the first part, I will talk about how we construct information models, how we encode them, how we verify them using our tools. Then Jan Martijn will talk about how we model processes and we capture them using patronage, not using BPMN models as we showed to you on the previous slide. Also, Jan Martijn will talk about the connection between information models and process models by means of transactions that we attach to different transitions, so we can manipulate the data that is stored in the information model, and then we will talk about future directions. So information modeling, we model information with finite sets and first order logic. So ORM is just a visual interface. Behind the scenes, we operate with finite sets and first order logic. Finite sets, why finite? Well, because we want to store at the end all the facts and all the information on a computer, and computers have still finite resources. So and actually it's enough to cater for many real world applications to store finite sets. And first order logic, then we use first order logic to define domain constraints over those finite sets. So information model consists of entities, relations, and constraints. Entities here are boxes with rounded corners. Relations of facts, these are boxes with sharp corners, and constraints are modeled with these all the purple elements that you see on this diagram. Those would be ORM constraints. And then if you want to define a population, well, then put a set of instances of an entity. Well, for each entity, we need to specify a set of instances. For example, we have 3 entities in this diagram: supplier, order, product, and then the set of elements S1, S2 defines the set of suppliers. We have just one order or one, and we have 2 products, P1 and P2. And the facts, they also specified as well as a tuple, so predicates over the elements of the sets that define the instances. And we can, for example, have a predicate supplies, which tells us that the supplier 1 delivers product 1, so supplies product 1. So this is how we represent models. And then also we can specify constraints, or different types of constraints, mandatory uniqueness, subset constraints. So there is no really limitation on which constraints you can specify, as long as they expressed in first order logic. And then once all the whole model is described, we use automated theorem proving. So we developed our in-house theorem prover that validates and verifies that no constraints are conflicting, or the population, so elements, instances of our information model, they don't violate any constraints defined by the information model over here. Okay, so let's start building a web shop. So this is a scenario we'll be trying to walk you through. So a small web shop offers products which sometimes may not be available for ordering. Customers can start an offer and add some products to it. Once the shop accepted the offer will be delivered. Meanwhile, the web shop sends an invoice which is paid by the customer. So it's kind of a trust model here happening, right? We send the order before we get the payment, and we trust our customers. If the customer doesn't pay, so if you trust too much from too many people, but some customers don't pay, at least 2 reminders are sent before the customer is blocked. So we need to send 2 reminders, and then if we still don't have payment back, we will block the customer. So I emphasize this constraint because I'll be just concentrating on this aspect when I show you the information model in a tool. So if we have 2 reminders sent and the customer doesn't pay, we can block the customer. Blocked customers may be unblocked by the web shop. And the task is to design an information system for this web shop. So step 1 is that we want to develop our information model. So we want to understand which constraints we want to capture. And we start with entities. So for example, we represent an entity offer, and then we add another entity and a relationship between entities. So we capture that offer and customer are in the relationship. So offer can be for a customer. At this stage, we capture many-to-many relationships, or end-to-end relationship, but probably we want to further specify that one, saying that offer is not for 0 or more, but for at least 1 customer, and therefore we add this C1 constraint, which is called the mandatory role constraint in our language, saying that, okay, so the now offer is for at least 1 customer. And probably that's also not enough. We want to say also for at most one customer, and then we need to add the uniqueness constraint C2, and we draw it as a dash, such a line over the element of that relationship that we show in the diagram. We add another relationship between offer and product. So offers can contain products and one many-to-many relationship at this stage. Now we specified further, so at least one. So offer contains at least one product. So we also add the mandatory role constraint C0. Right, we cannot have empty offers, so they need to contain some products. Then we can specify a lot of relationship that relate to the offer, right? We can say that offer is paid, offer can be accepted, offer can be delivered. Those are unary relationships, right? So basically unary predicates where we classify offers as paid, delivered, or accepted. Also, we have a binary relationship between reminders and offers. So reminder can be sent for a certain offer. And also, if I just fast forward, here we want to capture exactly the same pattern as over here by saying that, well, reminder, there can be like an empty reminder. Reminders need to participate in the relationship with offer. So if we create a reminder, it relates to a certain offer, and we don't create two reminders for the same offer, right? So that's what we capture. Here, also another type of constraint, an offer can be delivered only if accepted, right? So that's also quite clear from the domain, and we do that by adding so-called subset constraint, saying that if we have a delivered offer, it should also be accepted, right? So we can have delivered but not accepted offers in our system, and a customer can be blocked. That's a unary relationship that also appeared when I did the last click on this slide. So this is our information model, and then we can of course specify all those visual elements in terms of first of the logic constraints. So there are different types of constraints that just classify them based on the structural characteristics. There is a class of typing constraints. So for example, those are very simple constraints. We need to specify that elements belong to a certain entity type. So for example, for each sent reminder for certain offer, so if I have a reminder R sent for offer O, well, I also need to be sure that R is a reminder and O is an offer. So just basically simple typing. At the end, we just need to generate, we can actually generate this constraint automatically from diagrams, but we don't have this support yet in the tool. So actually also with students, we request students to exercise and develop those constraints. So it's also kind of was done partly on purpose at this stage. Mandatory uniqueness constraints, very simple. So here I'm saying for every reminder there exists element O that is an offer, such that that reminder is sent for that offer, right? So that's basically encodes mandatory constraint C3 in the diagram. And uniqueness constraint, I can say, well, if for every reminder and for every pair of offers, if that reminder was sent for offer O1 and offer O2, then offer O1 and offer O2 must be the same offer. But that captures this uniqueness constraint C4 in the diagram. So basically, we can describe the whole information model as a set of first order logic statements as a first order logic theory, essentially. And that's what basically we do at the end. And subset constraints, if you want to capture constraint C5, we just write first order logic statement. For every offer, O, if it is delivered, then implies that it's also accepted. And the last class of constraints, basically those we call those domain constraints. These are constraints that don't have corresponding visual notations, right? I hope it's not a surprise for many of you that information modeling languages like ER diagrams or M diagrams, they have visual elements, but there is a limit to where we can apply those visual elements. If you want to go and create some wild constraint, well, we will need to create some wild visual element for it, and basically ER diagrams or M diagrams will not contain such wild elements. And the only thing we can do, we can just use well, some scripting language, some other formal language to specify that constraint. So we just continue with first order logic. And here, for example, this is an example of constraint that asks to check that if a customer does not pay, at least 2 reminders are sent before this customer is blocked. And so this is a long, scary first order logic formula. Well, I hope it's not that scary for at least some of you in this session. So this is how we model information models. Then we actually do all these things with first order logic and entries and checks in one of the tools of our ISM suite, which is called It's a True World. We have different opinions on the origin of this name with Jan Martijn, but we maybe can discuss it later in the discussion session. But so basically what it is, we have a first order logic prover over finite sets implemented in them tool, and then we can, using an interface, create different constraints, create different populations, and verify if the population satisfies the constraint. So I switch now to the tool, right? And I can open some information model. So we prepared a file here. So I'm opening something that was prepared before this session. And what we see our 4 entity types. So we work with entities offer, product, reminder, and customer. And also we see the instances for different entities. So offer, there are 2 instances, O1 and O2. Product, there are 3 instances, P1, P2, and P3, etc. We can also see all the predicates, all the relations. So for example, here we have a relation send, and the send relation, we have that reminder D2 was sent for offer O2, right? So for example, here we say that reminder D1 was sent for offer O1, etc. And on the right-hand side, we have all those first order logic constraints that we develop inside of that information model. And if I can, for example, click visualize and also examine those constraints visually, right, as a tree structure. So this one is a typing of the send relation. So this one says for all reminders D, and that for all offers O, there is an implication if it holds that D and O are in a send relation. So I send reminder D for offer O, that implies that conjunction holds that O is an offer and D is a reminder, right? So that's fun. That's a constraint I also demonstrated to you on the slides. Okay, so let's go now and add one constraint, because this model is almost the full model that I showed you on the slide, except of this constraint C4, the uniqueness constraint C4. So I need to go back and create it, and I will just, if you allow me, copy and paste it. So just for the matter of time, so I don't need to type the whole first of the logic string. So that one says that, also I showed you this constraint on the slide. It says that for all the reminders D, if I have O, and for all pairs of offers O1 and O2, over here it holds that, well, if reminder D was sent for offer O1 and reminder D was sent for offer O2, it implies that O1 is equal to O2. Right, so that's basically the uniqueness constraint C4. I can also visualize it if I need to. Sorry, it's now visualized on a different screen. To visualize it, I can now add it to my set of constraints. When I add it, I need to specify a name. So for example, I'm typing C4 uniqueness offer for customer, and then I click OK, and I have it now in a list of constraints. But now I have an error, because some of the constraints, some constraints are violated by the current population. So I can explain the violation, right, using this very intuitive explanation, captured again in the first order logic, again also for the purpose of educating our students. So basically, this is the trace of the proof that the negation of the constraint holds, right? So the constraint doesn't hold, and this is the explanation why it doesn't hold. And here we say that, well, we have O1 and O2 such that reminder D2 was sent for both of them. So uniqueness constraint is violated, And if I go back to the population, then I will see that, okay, here we have a reminder D2, and right, it was sent for both offers, O1 and O2. So to fix the problem, I can just modify my population slightly. I just remove that entry, that fact from my information model, and well, that constraint C4 now becomes green, so it is correct. So we want to be green, we don't want to be red at the end, but we now violate another constraint. We now violate this domain constraint of having a blocked customer for which we haven't yet sent 2 reminders, right? So here we have a blocked customer C1. We have a blocked customer C1. For the customer C1, we send offer O1, and for offer O1, we only send reminder D1. So there was only one reminder in relation to the offer O1. So to fix that, because I have 2 reminders, I'll just remove this entry, and I will just add another. Sorry, I pressed the wrong button. Over here, I need to enter another fact. So I need to say that reminder D2 was also sent for the offer O1. All right, and now everything becomes green. We actually so our population satisfies all the constraints of our information model. So we can develop information models visually, but kind of in a tool, at the moment we define them as a collection of first-order logic constraints, and then if we have a population using our theorem prover, we can verify if some constraints are violated. We can explain why the reason that certain constraints are violated, etc. So at this stage, I finished my first session where I explained how we derive information models, and I will pass to Jan Martijn just in a couple of minutes. Maybe there are some questions at this stage, so let's have a small break and see if there are questions to this part of the tutorial, and I'll try to answer them.
So yes, there's a very interesting question about similarities with other tools. And so Petrus Papaganitigu, sorry for your pronunciation. Let me see whether I can give you the mic so you can quickly ask.
Yes.
Hi, can you hear me?
Yes.
Yes. Yes.
Oh, thanks. Thanks for the effort to pronounce my surname. So that was okay. So I'm asking because this kind of logic and the kind of rules that you're defining look remarkably like the kind of things that you would define in description logics to describe ontologies and so on. And those already, there are subsets of first-order logic, and they have already very efficient reasoning tools to do this kind of inference that you're doing. So, and I'm wondering, I mean, I understand the comment that, you know, you want to use first-order logic to be as general and agnostic as you can, but do you actually gain much from sacrificing this kind of efficiency in terms of what you can express?
So, so you're absolutely right? And kind of, we don't claim the novelty yet here, right? So we don't claim a novelty from using first-order logic to represent constraints and information model. The novelty of the whole approach will come from the whole combination, right, of all their components, right, all the 3 components, which give us a unique experience. So you're absolutely right. Yes, we kind of don't go for the productive system, so to say. It's more a prototype at this stage and used for teaching. And also prototyping ideas on how the systems can be verified, etc. So at this stage, yeah, you're absolutely right. There is no rocket science here. It's pretty much known content, but just well developed, we believe, in a very, very elegant way. So if you look at our papers, the way we describe the information model, we have very succinct formalism to capture all these things that I just demonstrated to you. That's also one part. But again, there is no rocket science here, only in the part of information.
That makes sense. Thank you.
Yeah. Any other questions?
Not really.
All right. so maybe then there'll be questions toward the end. So then, Jan Martijn, I will unshare my screen and pass control to you so that you can continue with process modeling and the link between the two.
Yeah, thank you, Artem. So I will continue with the second part, process modeling with Petri nets with identifiers. So in a way, I already assume that you know a little bit about Petri nets and formalism. And the interesting part of Petri nets is, as Petri once pointed out, that tokens point to some entities of interest in the real world. So that is basically what we want to take over. And if you saw this morning the presentation by Andre and Marco, then they already started talking about having identifiers. So what is basically the idea behind this is that if you model a Petri net like this, for example, here we have a treatment of a patient, then basically what we do in our minds is that we say, well, this token in the set here with patient resembles a patient. In available doctors, a token represents a doctor. In available rooms, the token represents a room, and so forth. And so that means that in our heads, basically what we do is we make those sets and we say, well, this token actually points, and so this token here points to this P1, the other token points to P2, we have a room that is pointing here. So in a way, we make those connections implicitly in our minds. And if you have a bit of a more complex structure, for example, here the token in the place treatment, and we have a token is representing a patient that is being treated in a room by a doctor. So it's a patient in a room with a doctor. Then typically what we do in our minds is something like this. And so this single token represents this one patient, this one room, and this one doctor. And basically what we want to do with Petri net with identifiers is to make this implicit thinking explicit. And so basically what we start saying is we start adding typing. And that means that, for example, this place over here is of type patient, because the tokens in here represent a patient. Here we have rooms, so the identifier are of type room. And if you have a treatment, then, well, this token represents a patient in a room in a doctor. Hence, we have three vectors on identifiers on the place. And then we use inscriptions on the arcs in order to create or to move the tokens and to bind all these values, the identifiers. And so basically what we say is, well, a transition is enabled if you can find a valuation for each of those variables, so whether we can point to those elements, and then say, well, if we can bind this, then we create a token over here with this patient, with that room, with that doctor. To create new identifiers, so to create new elements in our world, that's something we typically want. Then we use variables that are only bound on the output arc. So in a way, we can't bind it on the input arc, we can only bind it on the output arc, and that means that we can create new identifiers. And one of the very first papers that did this was by Fernando de la Rosa. And while discussing this, we noticed that in their formalism, there was only one token or one identifier per token. And while modeling, actually, you want to model those relations. So this is basically what we do in our Petri net with identifiers. So instead of having just a single identifier per place, per token, we have a vector of identifiers, and then that's the way we work with them. So to go to our example, how do we use this in our web shop? So we need to identify somehow what are the smaller processes, because, well, looking at this text and creating one huge Petri net is typically what we don't want. We chuck it into smaller pieces. So what we do is, well, if I look to this text, then I can identify some part about products. And so some products may be available or not. We have customers that can create an offer, add products to the offer, and well, then the offer is eventually delivered. We have a financial process because we need to send invoices. And we have something with customers because customers can be blocked and can be unblocked. So if we look to this process, we could say, well, there are 4 process models that we can look into. So if you model those, and you could model those in BPMN or in Petri net, it doesn't really matter. Here I have some 4 simple models for each of those processes. So above, we see the process for customers. So we create a customer, we can activate, or we can block the customer, we can activate it again, and we might even delete it. And similarly for offers, so we can create an offer, we may add some products, we can accept it, it will be delivered, in the meantime it needs to be paid, and then the offer is finished and can be archived. And well, the financial process, we can create an invoice, and as long as it's not being paid, we can send some reminders. And if after some reminders it's still not paid, we just block the customer. And so this is a very simple way of modeling PetriNet, and nothing new into this. There are many great ways on how to model those. But if you start thinking again in terms of BPMN, then you could also start looking into, but what actually do these places resemble? So what we need to do is we need to start looking into what are those types that we can use. And basically, if we see here, so we have a product process, so it's about a product. We have offers, so it is about an offer. We have payments, so it is about payment. And we have customer process, so it's about customers. So that's also a nice way of thinking of those identifiers. And you could also already have seen them in the data model. The information model provides this side of links. So we could say, well, we're going to add identifiers. We have customers, we have offers, we have products, and we have invoices. And basically an offer and an invoice is exactly the same. So we just say, well, that is equals to an offer, so I don't make a separate entity for this. And then you can start coloring the places. So we get a model like this. And basically all the places are now colored, and I left out all the variables because that makes the model very cluttered. But basically if it's connected to a blue place, it says, well, I move a customer. If it's a yellow place, I move an offer, etc. So this is in a way very simple, moving, adding the cases that you would normally think of in BPMN. You now add them to the PetriNet. As a next step, we can start integrating those models. So the idea is then to ask, so where are the interactions between those models? And so for example, if I look into those models, then I can only create an offer if I already have a customer. So this create offer transition requires that there is some customer. And so we can model that with this arrow over here. Similarly, we can say, well, a product can only be added if it's available. If it is unavailable, then we can't add it to the product. So we add a byflow. So this means just an arc going one way and the other way. So this is just a shorthand for the slide. And similarly, we can say, well, if the offer is accepted, then we don't just pay the offer over here. We really start the invoice process. So instead of having this arc over here, I just start the process over here. And once it's finished, I move it to here. So basically this whole pay offer process that I modeled here as a single transition is this whole process, so I just remove it. So nothing new here yet. You just think of terms of processes and how we can link those. So we can model this also in our tool, but first we need to ask ourselves, where do all those items come from? So if you look, for example, here to this transition create customer, then if we model it as a workflow, then there's an initial place that contains a single token. Whereas actually you want to say, well, create customer creates a new customer that was not yet there before. So what happens if you start modeling it this way is, in a way, we start thinking of which transitions can create identifiers, and we remove those. So in this case, the create customer, create offer, and create product are the candidates to say, well, those start new cases. And then we get a model like this. And now you already see that we run somehow in troubles, because now from moving from a bounded model, we move to an unbounded model. And typically what we do in PetriNet analysis is that we just say, well, if this model is correct, then somehow we assume that this model will also be correct. And that is a big step in analysis that you want to see, well, is this really the case? And what actually happens? So for this, to model this, to see what's happening, we created a tool that's called the ISM suite, the Information Systems Modeling Suite. So let me move to that tool. So now you see the tool over here. There are 4 processes that you can see over here. So above we have the order process. Here we have the payment process. Here down here we have the products process, and we have the customers process. And basically what we can see over here is that, well, we have this place over here, and it is typed with this offer. It consumes an O. It moves an O to accept offer. We have create offer that consumes that produces a new offer, and it is linked to this place C over here, which is actually, this is called what we call a reference place, And basically it points to this place over here for the customers. And so we can see this if we move down here to the properties. Then we can see in the references that we linked it to the place customers, which is actually this place here. So the ISM suite allows you to model those PetroNet with identifiers and create different diagrams. And so the different diagrams are shown here. We have the 4 pages, as they are called in PetroNets. So 4 pages with the 4 processes, and they are over here modeled. And we can start simulating this. So we can first ask, is it valid? It doesn't contain any errors, and if there's an error, so for example, if I would remove here the offer, I can validate again, and then it gives some ideas of what could be wrong. So for example, it says there's an ARC inscription, and well, the number of identifiers that are expected is different from what was received. So it provides some indications on how to repair this. So let's quickly undo this. And let's just start simulating. So I can validate again, and I can start simulating this model. It doesn't show the simulator, so quickly open the view. So here you see the PetroNet. At the moment, create offer is not enabled because this place customers is empty. So we're first going to register a new customer. So let's create a customer. So to fire, you can click on a transition, and then you see a new binding for which the transition is enabled. So we can click on it, and then customer gets a token, and then create offer starts to be enabled. So basically now can start the offer and click through, and then the whole process, and you see now the invoice process was started over here. So in a way, ISM Suite allows you to model those PetroNet with identifiers and to see what happens. So you can just click through this, see what happens. But as you might notice, for example, if you create a new offer and I just click through, I didn't add a product over here because there's no product yet. So I can create those products, and now add product becomes enabled as well. And if you would now just model it this way and look into your data model, then we already see that this somehow we have here new behavior that we wouldn't like to have, because in a way, the data model, the information model that we just created, adds these constraints. So in the next part that we're going to do, we're going to look into, where is my presentation? Down here. So here's the tool. So what we're basically going to do is we're going to link the data and the processes with a specification. So in a way, I already said what happens if you have this intuition. Then you could also say, well, this treatment is not just pointing to a patient, a room, and a doctor, but actually it is a treatment. So I could also say, well, that is actually this fact over here that is called treatment. And so this a patient in a room with a doctor actually just says, well, there's a treatment. So we could also say this start transition has a transaction connected to it, and the transaction states that we are creating a treatment. So that is the link that we have between the two. So here you see a transaction. It is the start treatment, so it's the start for this transition. We insert a patient, a doctor, and a room. So basically those are all the variables that are connected to the start transition. And we insert a tuple PDR into treatment. And if we execute this transition, then a new fact is added to our population for treatment. So this is the whole idea of specification, and we can look into our specification, see what happens for the web shop. So here we have the web shop again, and I slightly moved a little bit so that you can see both the data model, the information model here, and the processes. And all the elements are there, and we could say, well, what happens if we do a pay invoice? So we can create a transaction, and we just say, well, it's a pay invoice. It takes as input an offer, and we insert the instance of O, the element O, into the paid predicate, the paid fact. So this transition creates a new fact, paid. And you can do this for all of the transitions. So let's move to another one, send reminder. So basically what we want to do is, if we do this send reminder, then we want to create a new reminder. So we want to insert a new element into the reminder set and add all the relations into our population. So what happens is we have a send reminder, so we get a reminder, we get an offer, and we need to register it. So register R just means we insert the tuple into our, and we insert the element into the set of reminder, and we also insert the fact R into reminder, and we insert the fact RO into send. So this last one creates the fact send RO in our population. But somehow we have a problem, because here we talk about an R. So there's an R reminder. And as you can see in the process model, we only have the connections to this yellow places here for the offer. So that means we need to have this R variable as well. So how do we solve this in our notation? So we make this explicit by having a place. We type it with reminder. And we say, well, send reminder adds this variable R. So it creates a token in this reminder place. And notice that this becomes an unbounded place because we do nothing else with reminder. But it makes very explicit that this send reminder transition creates a new entity. So now we have this R bound, and we can register them. The most interesting one to discuss is for block customer. So if we have a customer and we want to block it, you see a transition block customer here in the pay process, and you see a block customer in our model for the customer. And basically this is the same transition. So we want those two to be the same. So basically we only want to block a customer if a token is here in the customer, and we want to block it from the invoice. So if you look into the transaction is quite simple. It just says, give me a customer and I will add a C into the blocked fact. So this creates the fact blocked C into the element over here. But we need to connect it with this transition over here. So for these transitions, we want only customers to be blocked if there's an offer over here. So we have the connection between, we need a connection between the two. So how do we do this in a Petrinet? So in the Petrinet, we couldn't say, well, create offer, create another token. And here in this token, we store that this customer created this offer. So you could say this place here now becomes a data store in BPMN terminology. And when the offer is finished, we just remove the token over here. So these are all the open offers that are not yet finished. So what is the token that we create? Well, we get a customer from the create customer from this place. We get an offer that we generate over here. So get tokens with a C and an O here, and this O is the same as here. So we create a tuple CO into this place. And then finally, this offer is being removed. This token is being removed when finish offer fires. And now if you want to block the customer, then we can link this block customer transition to this place over here with this byflow arc again. So this way we can check the offer that is lying here with the open offer over here and the customer that needs to be blocked. So this way we can synchronize the firing for this block customer. And here in a way you see that in our process modeling, we need to somehow blur the process model. We need to add all kinds of elements in order to really simulate what in the information system is happening. So let's move to our model. So let's see how the model looks like in ISM Suite. So here I have the model. Here you see the customer offer place standing. And well, if you look carefully, then you see that this transition block user is white. That means it's reverse. So again, we can see in the properties window down here, there's a reference. I should make it a bit larger. Then you see here transition block customer. So this is actually the same transition. So now we can start simulating again, and we can start using the population. So we say, first we want to validate, show you there's no error. And then we can say, well, let's start the simulator. We select the world that Artem just created with the web shop. So we select that file. We open a specification. So the specification is actually this file. Let me see, it's this file with all the transactions. So basically for each transition we created a transaction. So here you see accept offer. So this accept offer basically is this transition down here, accept offer over here. So it is linked via the IDs. So here you see accept offer, so it knows how to link those transactions. So let's connect them. Select the world again. I select the specification. I press OK. And now it says I couldn't find the transaction for the place products because product contains some tokens. And basically what the editor does is the simulator asks, checks for also for places if there's a transaction in case there are tokens. So you could populate your database initially. You just press OK now. And now here on the side, you see the current world. So we call it a world with all the populations. So all the facts. So for example, you have an offer 01 and 02. You have 3 contains relations. So offer O contains some products. And now we can start simulating. And as you can see now, register customer is enabled. So this one can create a new customer, because if we look to the specification, then we see here with create customer, it registers the C. So it creates a new element into our population. And it also creates a new fact for that customer. And as this transition is now enabled, it means that both the transaction results in a valid population. So that the world or the population satisfies all conditions, and also the transition is enabled. So we can fire it. So it says, well, I can bind with a new variable E1. So it creates an E1. And as you can see now in customer, it created the E1 fact for customer. And again, I can also create a product. So I could create a new product. I can make a product unavailable. But as you notice, if you look to the model and the transitions that are enabled, there are no red transitions in our offer process about the order process. So basically what it states is I can't start create offer for new customer and I can't create new offers. So what is happening here? Why do we see this? So if you go to the warning step, then here it explains why create offer could not be executed. So basically the check that Artem just showed in It's a True World with explain me why this transaction or why this is violated, why this constraint is violated. We get here a message that the constraint C0, the mandatory offer contains product, is being violated. And similarly for create offer for new customer, we have the same, and there's a violation for this conjecture. So we now created an information system with a specification, but if we combine the two, then we see that the whole information system is actually flawed. And why is that the case? Well, basically it is the case because this mandatory constraint for offers to products is being violated. So how can we solve this? So how can we solve those problems? So there are several ways that we could repair all those elements. So for example, we could alter the specification to guarantee constraints. So basically what do I mean with this? Well, we have here this create offer transition, and it says just create offer, give me an offer, give me a customer, and I will register the new offer and I insert all the facts into the population. But actually what is needed is that we also have here this C0 constraint. So we could also just say, well, we need to insert this OP into contains. So we need to add this variable P over here. We get a create offer with a by float available products as well. So to show that solution, here we have that solution. So now you see I have here a create offer for new customer, and it is linked to this product space place. This product place is actually this place down here with the available products. And as you now can see, I can just say, well, I also need a token from this product place, and it's labeled P, so I can add this fact to the population. So to check that this really is working, I can start the simulator again. I can take the update specification repair, so I just keep the same world. I have a new specification that states I also need to insert this product when I create a new offer. And then we can start looking into the model again. So I can get this warning for the products. And here we have our current population again. And as you can see now, this create offer for new customer is enabled. So if I fire this transition, what will happen? It will take a product, it will create a new customer, and it will create a new offer. So let's see what could we do. So there are 3 different bindings because there are 3 different products. So we could say product P3, P1, or P2. So let's just take product P3 and we fire it. And now you see indeed that we have a new fact here, contains E2 for the offer. E2 contains now product P3. And now we can just continue, accept the offer, and continue the process. So this is one way of solving this whole problem. But there are different solutions possible as well. So I could also have another solution, say solution 1, and I could ensure that the process model guarantees the constraint. So one solution could be that I just dislike this C0 constraint in my information model, and I just remove it. So I just remove it. This is my new information model without C0. And then I need to tweak the model over here to have another add product transition. So I get an add product and an add first product transition so that I can ensure in my process model that once I accept the offer that I already added a single product. So how does this solution look like? So here we have the model, and as you can see now, there's an add first product in between that is connected to the same products transition. I can now select the same world, so I can select the new world. I add the specification. And as you now see in conjectures, the C0 constraint is being removed. So C0 is not shown anymore in all the conjectures. So that means that I don't check anymore whether an offer contains at least one product. But I ensure that the product, that it only gets accepted if there's at least one product by this add first product. So we can show this, and so we can create the offer for this new customer. We add the first product, we can add a second product, we can add some more products, and then we can accept the offer. So now the process model really ensures that my data constraint is being maintained. And of course, we can think of some more solutions. So another solution would be if I just take the model and I remove the C0 constraint about an offer contains at least one product. And instead I just say, well, when do I require to have at least one product? That is when the offer is being accepted. So I could also say, I just say, if this is accepted, only if it is accepted, then there needs to be a product that is being contained in this offer. So I add a domain constraint that says, well, if it's accepted, then there should be a product. So again, I can make this solution. Let me see, that's this one. So it is the old process model. There's just this add product transition over here. There's the accept offer. I can start simulating again. So select the world. Instead, I just select the world with the update data model. I take that solution. I take the specification. I don't need to change it. So this specification is exactly the same as the very first solution that was wrong. And the only change is that I have this extra constraint in my world. And as you can see now in conjectures, there's an extra domain constraint. Let me see, where is it? It's here, D2. So a domain, it's a domain constraint, accepted offer contains at least one product. And I can simulate the model, so I can say, well, create offer for a new customer. I can fire it. And as you now notice, accept offer is not enabled. And if I want to know why, I look into warnings. And there you see for accept offer that the transaction indeed violates the conjecture. So only if I add a product, let's say P3 again, now it suddenly becomes enabled because there's a product added to the offer. So in this way, you can look into the warnings, see what happens, and why certain transitions are not allowed in the complete information system. So now you've seen 3 types of solutions. You've seen 3 different solutions for this problem to repair. And that basically also shows how do you decide what is the best solution. And that is a nice introduction for the future directions. So I hand over to Artem again.
Thank you, Jan Martijn. So can you click to the next slide, please?
Yep.
So basically you've seen this machinery, right? So where we can balance the constraints between the information and the process model. And so now once we have this machinery, we think of a couple of applications or interesting areas to explore. So for example, right, so we can have a completely correct model, information model separately, look at it separately, and we can have a completely correct process model if we look at it just on that process model. But when we combine, we can get some redundant constraints. Like, for example, what Jan Martijn showed to you, right? So that constraint between an offer and a product, and that offer must contain at least one product, that mandatory constraint. Well, we can have that purple dot, mandatory role constraint dot, in the information model, and then we'll be ensuring that constraint in the information model. But we can also have a transition which ensures that that constraint is never violated, right? So that can happen, and then that constraint in the information model becomes redundant, right? So we basically check it every time we update the population of our information model, but that constraint is simply redundant. We don't need to have it. So, or vice versa, we can have some constraints in the process model that say I require that something is executed in a sequence, A before B, for example, but the information model will ensure that well, actually allows us to execute those actions A and B in any order. So that's a constraint in the process model becomes redundant. So we can go both ways here. And that's one area that we want to explore, redundant constraints that become redundant once we combine the information model and the process model together. And if you go to the next slide, Martijn. Yeah, and another problem is how to balance the constraints, right? So here you see actually three information systems. All the three information systems on this slide, they share the same information model. They're shown in the middle bottom of the slide, right, with the entity P and the fact Q. So this is our information model. We have we have transactions for transition A and B. They're also all the same for all the three information systems, but all these three information systems differ in their patronets and their process models, right? So on the one on the left is completely data-driven, in a sense that data constraints govern which transitions get executed, so which actions get executed. And the one on the right-hand side is kind of another extreme, which is where now the execution of actions, transitions, is just dictated by the semantics of the patronet, general patronet semantics, right? So data constraints just correspond to those semantic, and they just follow. And in the middle, you have somehow the hybrid approach, right, where we combine the two approaches, and there is a spectrum of all those systems in between those two extremes. So the question is, which is the best solution? Where to put constraints into the process model, into the information model? What are the suitable methodologies? So this is also the other area that we want to explore. So these are our ideas for future work using these machineries that we have demonstrated. Okay, so this is, I believe, almost the last slide of today, right, Jan Martijn? Yeah, so this is the conclusion slide. We love playing with this interplay between data and processes. We demonstrated to you how our information system is composed from an information model, a process model, specification of transactions for all the transitions. And I hope you also agree that this area requires much more attention, much more results like these two problems we demonstrate to you. We also want to hear your opinions, what you think about these problems. Maybe you can also suggest us other interesting ideas to explore. Okay, thank you very much for your attention. We are open for questions.
Yeah, and I see already a first question by Manfred. So I just give the floor to Manfred.
Yeah, okay, you can hear me?
Yes.
Okay, fine. I fully agree with you that a strong linkage between data on one hand and processes on the other hand are of utmost importance for information systems modeling, but also engineering, to have really a running system at the end. And the work that you presented is very much related to what we know as artifact-based process modeling, or object-centric, object-aware process modeling, where very often, let's say, we have an information or data model with the entities and the semantic relations between them, including cardinality constraints, for instance. And on the other hand, we have the processes, and usually two levels. The small processes, often expressed in terms of object life cycles, not modeled, usually not modeled in terms of Petrinets, but maybe more in a state-based fashion, like using some kind of automaton. And then, of course, also the coordination of these many small object life cycles needs to be handled. So how would you relate your work, which is still a bit more on the modeling level, as also emphasized in the title of your presentation, with respect to these works that also target at process runtime support?
Maybe I can start with an answer. Thank you for the question, Manfred. So maybe the way Jan Martijn was presenting our scenario, right, by splitting the process over these kind of objects, suggested that this reminds of artifact-centric approach, and in that case, yeah, it really does. But the formalism and the approach is much more general, right? So you can, like in this scenario, this last slide that we showed, where there is a spectrum, right, where the pattern is basically a flower model and everything is controlled by information constraints. There, it's very hard to make a link to where this is an artifact, right? So it's kind of a very blurred model with a random, well, not random, but very engineered constraints to derive the required behavior. Whereas on the other side, you have like a fully fledged process model where, like, the way we used to model processes without any data constraints, any data requirements, etc. That would be like a classical process model without any artifacts at all. So that scenario that we demonstrate, yes, it suggests that it kind of reminds of artifacts, but in fact, it's kind of more general, right? We can model artifact-centric approach. We can model.
That's what
more,
I agree with. You're
yeah.
right. But for instance, when looking at the information model, and that was my first question I would have liked to ask after your first part, I didn't see attributes belonging to the entities, and some approaches, they're even at that fine-grained level, the object-driven or data-driven approaches that not only consider the states of the data objects, but also the attributes, and then the presence of some attribute values determines whether or not a certain state is reached. And you can utilize this knowledge on the relation between attributes and states also for the data-driven enactment of object life cycles, but the entire process structure as well. So why did you not consider attributes and values of attributes, etc.? Makes everything much more complicated, but maybe you consider them.
Like, in which way you suggest it makes more complicated? If you consider attributes, or if you don't consider attributes?
I think you will win something out of it, but I'm not sure whether or not in your approach you consider attributes. You have these states. That's what I can see. You have delivered and accepted. These are states of offer, of the object offer, for instance.
Okay, of course we can also describe attributes through the relationships, right? So there's these facts. We can describe attributes. It's just kind of not as a first-class citizen in our formalism. And again, the discussion what is preferred, I think, is a very complicated discussion that requires more empirical evidence what is preferred. So, but we can model attributes, right? So we can have not only this unary facts, right? But we can have, well, basically fully blown information model where we will capture also attributes. Yeah.
Thank you.
Thank you.
Yeah. Then there's an interesting question by Michel Brunings. And he asks, so what is the advantage over this modeling language over CPN tools? And
do you want to start, Jan, one time? Do you want me to take this question?
yeah, I think maybe it's easiest to just quickly think or discuss why we didn't use CPN tools, because well, in a way, for us it is like shooting with an elephant on a mosquito, as would be a Dutch saying. So in CPN tools you can model anything, and but process is the main citizen in CPN tools. So that means that you have to somehow encode the whole data model and all the constraints into your CPN model. And of course you can do so, but then you lose the power of having the information model where you can very easily model the data constraints, or have some data analysis that is making your information model, and a process model that creates the process models. So if you use a full-fledged colored Petri-net notation, then you're directly with saying you're using a complete computer, and analysis becomes very difficult. And the other part is, if you have to teach it to students, or if you want to use it in practice, then CPN is a very nice formalism, but you need a doctorate in order to model those process models. So that was our consideration of moving to just Petri-net with identifiers. I hope that answers your question, Mitchell.
Well, I mean, we had colored Petri-nets in a bachelor course. So I disagree with you need a doctorate for it, but I understand that you want to emphasize different parts.
Yeah.
Yeah, so basically our formula suggests a bit of different balance, which is less general what the colored Petri-nets would be, but also sufficiently expressive to capture most, well, basically all currently available information system. You can still model that, and also with that formalism, you can have some analysis results, right? So for example, in one of the papers we demonstrate that reachability is decidable. So basically, we can decide that certain state with certain population is reachable. That problem is decidable, super complex but decidable. Given one constraint, I mean, there is always but we need to set an upper limit for the identifiers, right? So if I say, can I reach a state up to identifier 1 billion? We can do that, right? You can model an information system with, well, where a process model has describes infinite possible states, infinitely many possible states, right? You have a fully blown database with insert, select statements, update statements, etc. And you can have a decidability of the reachability problem, given that you always bind that kind of population and database up to a certain index, up to a certain identifier. So that's a benefit of, well, difference with the colored Petri-nets.
Thank you very much.
And then I would like to give the floor to Andy.
Oh, all right. You hear me, right?
Yes.
Okay.
Yeah.
Thanks, Martin. Guys, thank you very much. So I finally understand much more about the approach. So it's actually very interesting. And after having, I hope, carefully listened until the very end, I get somehow I confirmed for myself a certain point here. So when you're modeling your data part, right? So you're having your ORM model. Does it account for volatile data or persistent data? Or is it just all the data that you're having in your process? So why am I asking you? Because we usually don't really think about, the types of data we're playing with. However, especially in the applications that Artem was mentioning at the very end of the presentation, I think considering this difference could have a tremendous impact on somehow the analysis that you would do over the models, and certain judgments that you would make about these combinations when you bring together process models and data models.
Mm-hmm. Yeah, so that is true. So basically what we look into is, well, we say we start with some initial population, and basically the identifiers that are in that population and the identifiers that are in the model, that's somehow the implicit connection between the two. So we model both volatile and persistent data in the ORM model. If you make a transaction explicit, so if you say, well, I make this fact explicit, then it is inside the ORM model, and then you can use it in your constraints. Sometimes if you want to have volatile data, it might be, and I showed it in a way with this place over here. Let me go in. Here with this customer offer place.
Yeah.
That is somehow volatile data. You could say, well, it is this for relation, but you could also say, well, this is just volatile data. So if I wouldn't have this part of the information model, then I can still store this volatile data to use it later on in the process. But I need to make it explicit in that case.
In fact, I wanted actually to ask here, so like say another solution would be to, let's say, synchronize those block customer transitions. Another solution would be just to add the information in, let's say, your, so to say, persistent storage in quotes, right? And then when you're trying to fire a block customer, you're somehow checking on the information that you have put about the customer and the offer into your database, and only after somehow you don't really encumber your process model with extra places used for checking.
Yeah, that would be a nice solution as well. So you basically add a constraint for blocked customer.
Because you see, so here is also the point about how would you like to synchronize the behavior of your net with your data?
Yeah.
And there are many ways, That's the point. That's,
yeah. And the other part, and that's maybe also important to realize, if you would make this solution as you suggested, then block customer this transition here in order to only fire it if some data constraint is valid. That's in a way impossible to do in our formalism, because we need all the tokens that are there. So you would need then another data constraint that says something like can be blocked. So then the block customer transition would create something like can be blocked attribute, and then the can be blocked attribute should only if can be blocked should hold to be able to block. So you get some very cumbersome relations if you model it that way. See what I mean, Andy?
Yeah, I see what you mean, but that could be also some sort of the implicit constraint that you're having, right?
So here we try to make those implicit constraints as explicit as possible.
Okay, right. I see. Yeah, that's nice. That's very nice. So as Manfred was saying, so it's very much in the flavor of artifact-centric models, what you're having here.
Yeah.
So, okay, guys, if you permit me, just one more fast question, which was just about the verification, because Artem mentioned that you have done some experiments on it, or not? Am I wrong? So,
yes.
Is it available now in the tool, or if not, just some maybe more details about the experiments? Because I myself know about verifying data where processes in the databases, and I know the amount of mess it creates, and that this is almost untractable if you have bigger databases. So how bad was it for you here?
So I used the tool for new students. So they were first year bachelor students in the fourth period, so from April to June. So the last period of the year, and so they all used the tool, and the main problems they had was indeed thinking of what happens if I create this transaction and add the constraints. So what happens in the interplay? So especially the error that most students made was the error that I showed here. With the solution of the add first product. So having this add first product, or that this transition create offer could not fire because of all the implicit constraints. So by making this explicit in the tool, they really had a feeling like, oh, this is what's happening. So we need those constraints, or actually, do we really need those constraints in order to model what happens? So it gave them quite a lot of food for thought to see the constraints and the violations that would happen if they would fire a transition.
Yeah, right. But actually, you could also tweak it based on the property that you would like to check on the system, right? So you could just brush away all the constraints that you're having, saying that, yeah, okay.
And here I think it is also in the type of students that you have. So if you have computer science students with a firm background in logic and say automata theory, then that's quite doable and model checking. If you have information science students who have more a background in business and in creating those models, then it's much more harder to create those constraints manually. So model checking for them turned out to be very difficult.
Okay, I see. Well, thanks a lot. Thanks a lot for your presentation and the answers. Thanks, guys.
Yeah, we already started the discussion. We should continue, right? I mean, offline discussion about synergies, about with your approach and our approach.
Yeah, that's for sure.
Okay.
All right, Minsuk, are we on time? How are you doing?
Yeah, I think it's time to finish the sessions. And actually, I would like to ask you about the feedback from students, and I already got answers. And thank you for the nice presentations. So I learned a lot from your presentations, and I think many people in this session also have same feelings. And thank you very much. And thank you also for the participants. I think we had great discussions. Okay, thank you all of you, and enjoy the conference. Okay.
And maybe a last remark: if you want to use the tools, they are all available on our website on informationsystem.org. So there you can find all the material that we used in this tutorial, so that you can play them with yourself. And if you have questions, just let us know.
That's right. That's right.
Okay. Thank you.
Thank you.
Thank you, everyone.
Bye.